Hello everyone, this is Gary Templeton. I'm going to show you how to transform continuous variables to a more normally distributed variable in Microsoft Excel. As you can see here, I have a data set containing a variable of interest, the return on assets, or ROA, of a company. You can see from this histogram that this variable is extremely non-normally distributed. Furthermore, you can see that the skewness and kurtosis values are extreme. Skewness is negative 195.021. Kurtosis is 38,994.93. This is about as non-normal as you will find in the universe and cannot be simulated. These values are way outside the accepted threshold of 2 for each. This situation makes the variable of little interest in many statistical procedures because these extremely non-normal distributions will threaten test assumptions. To address this problem, there are two steps involved with the two-step transformation to normal. Before we apply any calculations to the data, the first thing we have to do is to make sure the variable of interest has the necessary precision. We need to look at a couple of aspects of this data. First, let's click on the column for return on assets, right-click, click on Format Cells, and let's set the decimal places. Instead of 2, let's have 8. The reason we need so many is because if we scroll down, you can see that we have 45,490 records in this data set. If we don't have enough precision for return on assets, then applying the first step will create a lot of ties. In other words, the percent ranks for return on assets will result in a lot of zeros and ones. These two values cannot be used in the second step, so we need to avoid that problem. As you can see here, return on assets is precise to 8 places to the right of the decimal. So let's proceed toward calculating the result of the first step, a fractional rank. We're going to call the result of step 1, step 1, and in parentheses we're going to include the label uniform because this will result in an approximate uniformly distributed variable. We will see this shortly. We'll place the calculation in this cell adjacent to the first value for return on assets. The formula is this: if D2, the value for return on assets, is equal to a null value, in other words, if it's empty, we're not going to perform this calculation. So if D2 is equal to null value, then null value. Otherwise, we proceed with the calculation. That uses the percent rank function. The inputs to the percent rank function are the entire series, in other words, D2 to D45491. This captures the entire data series for return on assets. Notice there's a $sign between the letter D, which notates the column, and the number 2, which denotes the record number or row. What this does is freezes the reference to this data series when we copy the formula that's in column E down, and we're going to do that in just a second. The next argument is D2, which is the actual value for return on assets that we will be performing a calculation on. And the third and final argument for this percent rank function is 8. This is important because it provides adequate precision for the result. Again, if we don't provide adequate precision, it will result in many ties for zeros and ones when we calculate step 2. So 8 will give us adequate precision for this sample size. Press enter, then we will copy down by double-clicking the handlebar. So now let's go look for the 0 and 1, which are going to cause a problem. I happen to have searched for this. I know there's a problem on row 901. And here it is. This value of 1 will not be allowed as an input to step 2, which is an inverse normal function. So we have to do something about this. What we will do is estimate this value. It can't be 1, but it needs to be close enough and reasonable. So what we're going to do is we are going to impute a value that is equals 1 minus, open parentheses, 1 divided by the sample size for return on assets. To calculate that, we use count, open parentheses, and select the entire series, And the simplest way to do that is to reference the entire column. That would be D colon D. Close parentheses and close parentheses again. Note that this value is reasonably close to 1, which is realistic and also allowable by the inverse normal function used in step 2. Similarly, we have another problem in the data set, and that is there is a value of 0 that resulted from step 1 that we also need to impute to be allowable in step 2. I searched to know that this value is in record 24691, which is right here. You can see that this 0 is not allowable in step 2. So again, we need to estimate it. We will use the formula equals 1 divided by the sample size. And again, we'll use the count function. We'll select the entire column D, close parentheses, enter. This value is realistic and is logically justified. If we did not do this, we would lose this record when performing step 2. So what I've done from here is I paused the video and I made sure that step 1 has no instances of 0 or 1. There was only one of each, which means the return on asset variable as well as the result of my percent rank were adequately precise. They produced only a single 0 and 1 and only had to fix 2 values. For step 2, a good variable name is step 2 normal because we're going to estimate a normal distribution. Note that the quality of the normal distribution resulting from step 2 will depend on the quality of the uniformly distributed variable resulting from step 1. This formula is as follows. Again, we're making sure there's a value in the adjacent cell, the result of step 1. If E2 is equal to null value, then null value. In other words, if E is empty, we also want this value to be empty. If not, we perform the inverse normal function using norm.inv, open parentheses, E2, the result of step 1. The next argument is a mean. We will set that at 0. And the next argument is the standard deviation. We set that to 1. And if you've taken some basic statistics classes, you recognize that as producing units of z-scores. That is one option. Another option is to set as arguments the mean of the original distribution and the original standard deviation. In that case, the result of step 2 would be in units of normalized original units or normalized return on assets. But in this case, we are producing z-scores for return on assets. This is useful in a number of statistical comparisons across variables. So this is our result. We could perform step 2 because there were no zeros and ones as a result of step 1. And now we can go look at the histograms for each of these. And as you can see, is the histogram I showed you earlier for return on assets. This is the result of step 1, and SPSS is the tool I'm using. It will superimpose a normal distribution. You can see that this result is almost perfectly uniformly distributed. And here you can see the result of step 2, which is almost a perfect normal distribution. Notice that the data is centered around 0, which was our decision to produce z-scores, and the standard deviation is close to 1. I always maintain that researchers should document their procedures. That would include describing what each of the 2 steps accomplishes. And if you need literary justification for using the 2-step, you can cite either one of these 3 articles. The first one in 2011 is a description of the 2-step published in Communications of the AIS. The second listed article, published in 2017 in the Journal of Information Systems, compares the 2-step with more prominent transformations as it pertains to achieving normality. So it is a proof of concept type of paper. The third, published in 2021, applies the 2-step in a theoretical domain useful to information systems researchers. It was published in the Database for Advances in Information Systems. I hope you found this video useful. Thank you.